to the Bellman-Ford algorithm. So now we know that the Bellman-Ford algorithm is based on dynamic programming, where we divide a problem into sub-problems, and then we try to find an optimal solution of a problem. Means the shortest, in this example, for example, we'll try to find the shortest path, right? The best path to reach from source to destination. So again, here we have some of the notations that we need to understand before discussing Bellman-Ford's algorithm in detail. So this notation dxy, d sub xy, is the cost. In fact, it's the least cost path from a source x to destination y. So here this x is source and this y is destination, right? So and how we can compute the least cost path from x to y? Yes, the least cost path from x to y is in fact a minimum of the cost to reach from x to its neighbor v, right, plus the least cost to reach from its neighbor v to destination y. So this means we have to identify a minimum path that is taken over all the neighbors of v. So what we will do basically is we will calculate this value for all the neighbors of x, and we will select a path where reaching from x to y is minimum from a specific neighbor. Okay, so if we look at this problem of finding the least cost using Bellman-Ford equation, so what do you think was the cost to reach from it's the same example, by the way, that we used in the last lecture. So what do you think was the least cost to reach from u to z, right? So what you will do, you will find the cost to reach x from each of its neighbors. So it will find the cost to reach z via v, right? To reach z via w, to reach the destination z via x, and it will select a path which is the shortest path to reach the destination over all the neighbors. And similarly, this will be happening distributedly on its neighbor as well. So x will again find a cost through its neighbor, which is minimum to reach the destination z. Similarly, we will also try to find a cost that is minimum through some of its neighbor, through one of its neighbor to reach the destination z, right? So what here we are doing is, so we are calculating the cost to reach from router u to its neighbor v, the cost to reach router u to its neighbor x, the cost to reach from u to its neighbor w. And it's, by the way, it's known why, because these are the direct neighbors of u. Now we will find a least cost, and same is the case with the neighbor x. So this cost is known, we know this cost 2, so we can see here, right? And similarly, this cost is 1, the cost to reach from u to x, and the cost to reach from u to w is 5, right? But what's the least cost to reach from v to z? So what's the least cost to reach from the neighbor v to z? Yeah. So the least cost from v to z is from v to x, which is 2, and then from x to z, which is 1 plus 2, 3. So 2 plus 3 is 5, right? So again, x also calculates its least cost to reach z, which is 3, and w also calculates least cost to reach z, which is again this path, right? From y to z, it's 3. So we'll select the shortest path, which is via neighbor x, right? So the shortest path is via neighbor x, right? So in this way, we'll try to identify, using Bellman-Ford, the shortest path that is taken to reach a specific destination over all the neighbors of the source router, which is u in this case. Right. So so this distance vector routing algorithm is distributed, means every node communicates only with the directly attached neighbors. It's iterative. There is no stop signal here. So it continues until there is no node to exchange information, right? And it's basically we always stay in a loop and wait for a link cost change that we'll see in a minute. So it's self-terminating, and the machines or the routers does not need to. The router or the nodes need not to exchange any information. So let's try to expand this notation, since we have seen that in order to reach from this source X, this is the source, remember, to destination Y, the important factor is the neighbor, right? So I have modified, so we have modified this representation or this notation, where now it is written as the cost to reach from X to Y via Z, right? So this is the distance from X to Y, where X is the source, D is the destination, via Z, as next to means Z is the neighbor in this case, right? So this Z is neighbor. Okay. So now if I want to calculate this cost, so what I have to do is, yes, first of all, I have to calculate the cost from the source to the neighbor Z. So this is what is happening here. So we have to calculate the cost to reach from the source to the neighbor Z, and then we have to again calculate the minimum cost to reach from the neighbor Z to destination Y via sum of its neighbor, say W. So again, Z has to explore all of its neighbors to see which one contain the least cost to reach the destination, and then we'll add these two costs together to find the distance to reach from X to Y via Z. So let's try to look at the algorithm first. So it also has two steps. This algorithm, distance vector routing algorithm, which is Bellman-Ford algorithm at the moment that we're discussing, it has two steps. It has an initialization step, right, where for all the adjacent nodes V of a source, if the node, the destination is not the direct neighbor of X, the cost to reach the destination is infinity, right? So this means that the destination is not the direct neighbor. And if the destination is the direct neighbor, the cost to reach from X to V is known. Why? Because V is the direct neighbor of X, right? And for all the destinations Y, what we'll do is we'll send the minimum cost to reach from X to Y, obviously sum of its neighbor W. So what happens in this initialization step is, again, we'll have the same, we'll follow the same steps as we did in the last class. So first we'll look at the algorithm, we'll try to solve an example, and then we'll again come back and try to understand the algorithm. So in this initialization step, to simply, if a node is directly attached with the neighbor, the cost is known, and if a destination is not directly attached with the neighbor, the destination is infinity. And then when a cost is known to reach a specific neighbor, so we need to exchange this cost with the other neighbor. So X will exchange this cost to reach destination Y with each of its neighbors. So after this initialization step, we enter into a never-ending loop, right? So what happens here is that a node waits for what? Until there is a link cost change to a neighbor V, or there is an update from neighbor V, right? So if a link cost between, say, router X and V has changed from 2 to 3, right? Or V informs the router U that a cost to reach a specific destination has changed. So if the cost to reach from X to V changes by D, I mean, this change can be, positive as well as negative. So we have to recalculate the cost to reach all the destinations, right? So else, if the update is received from V with respect to some destination Y, again, what we have to do is we have to again calculate the new cost, right? And if the new cost is minimum, we will send this update message to all of the neighbors of V. And we'll again we'll stay in this loop and we'll wait for two things to happen. Either a link cost has changed, that is the cost from X to V. So if it has changed, the cost has changed, we will recalculate the cost, right? Or else we'll wait for an update from V with respect to some destination Y. Again, we'll calculate the new cost, right? And if the new cost is minimum, we will communicate this update with our neighbors. So let's try to see how it works with the help of an example, and then we'll again come back and try to understand this algorithm. So, so what happens basically? So a node has to wait for a change in the link, number one, or a cost message from the neighbor. And then what we have to do is we have to recompute the distance table. And if by recomputing the distance table, we come up with the new least cost that we have to notify to all of our neighbors. So each iteration in the loop is caused by either a local link cost change, means the cost from U to V has changed, or there is a message from its neighbor that there is a new least cost to reach some of the destination, right? So each node notify neighbors only when, this is important to understand, when its least cost path to a destination has changed, right? And then the neighbors notify their neighbors, and then so on and so forth in a distributed fashion, right?